Hello everyone. In continuation of solving the exam sample exam paper, in this macro video I will solve the fourth problem. In the fourth problem, a second order transfer function is given, and in the first part of this problem is asking for which values of damping ratio and natural frequency uh, for or in fact how the location the values of this damping ratio and natural frequency omega n will affect the position of the poles of h of s. We also need to look for which condition the system the transfer function h of s will be stable, and for which condition h of s will have an overshoot in its response subject to the step or impulse input function. In order to answer these questions, first we need to look at the characteristic equation of the transfer function. The characteristic equation of the transfer function h of s is s squared plus 2 zeta omega n s plus omega n s squared. By putting this characteristic equation equal to 0, we can find the poles of transfer function. By solving this polynomial, we have the poles of the transfer function as s1 and 2 equal to minus zeta omega n plus minus omega n root zeta squared minus 1. Based on the value of zeta, we have different type of the system. Let's first assume that damping ratio is bigger than 1. If the damping ratio is bigger than 1, this such system are known as overdamped system. In overdamped system, since the all values we have here are real, minus zeta omega n is real, and since zeta squared is bigger than 1, we have the real roots here. So we have two simple poles on real axis. If damping ratio is equal to 1, this such system are known as a critically damped system. For the critically damped system, if you look at the poles here, zeta is 0, so this part will be 0. We have just the value of minus zeta omega n, which means s1 is equal to s2, which is equal to minus zeta omega n. So for the critically damped system, or for the system with damping ratio equal to 1, the poles of the system are repeated and are on real axis. Let's look at the condition when the damping ratio is less than 1. If the damping ratio is less than 1, we call such system as underdamped system. For the underdamped system, if you look at these values, zeta is less than 1, so the value under roots will be negative. So we have imaginary part here, and we have a real part minus zeta omega n here. So for such system, we have two complex poles on complex plane. And if damping ratio is 0, if the damping ratio is 0, this part will be 0, and we have just imaginary part. Such systems are called undamped system, and for such system we have two poles on imaginary axis. If we want to look at the effect of the damping ratio on the location of the poles, first let's look at the underdamped system. For the underdamped system, we have two poles, minus zeta omega n plus omega n plus minus omega n root zeta squared minus 1 j. Actually, we have two complex poles. So if we show the poles on imaginary plane, we have two symmetric poles. The real part of these two poles is the same, which is minus zeta omega n, and the imaginary part of the first pole is plus omega n root zeta squared minus 1, while the imaginary part of the second pole is minus omega n root zeta squared minus 1. Let's look at the angle between the real and imaginary part of these poles. If we call the angle between these two poles the real and imaginary part equal to theta, the cosine inverse of theta will be cosine inverse of zeta omega n, the value of the real part, over zeta omega n squared plus omega n root zeta squared minus 1, the length of this line. So if we simplify further this denominator, we will get the theta equal to cosine inverse of zeta. So from this relation, you clearly see that the location of poles is directly related to the damping ratio, and the length of the poles is related to omega n. Let's look at this when the damping ratio is 0. If we have the underdamped system, in this case theta will be 0, so these two poles these two poles will be on real axis. In another word, if we decrease theta, these two poles will be moved towards each other, towards the real axis. If we increase theta or increase damping ratio of the system, these poles will move towards imaginary axis and will get apart from each other. If, for example, look at the critical damped system, if we put the zeta equal to 1, theta will be 90. When the theta is 90, these poles will be on imaginary axis, and we have just two simple poles on imaginary axis. If we look at again zeta equal to 0, which we have the underdamped system, we have S1 and 2 equal to plus minus omega n j. So the poles will be on imaginary axis. And if zeta equal to 1, which means we have on critical damped system, we have the repeated poles as S1 and 2 equal to minus zeta omega n, which are on imaginary axis. In fact, here for these poles, zeta is 0, theta is 0, and for these two poles, zeta is 1 or theta is 90 degree. For the second part, we're looking for which case the system is stable. The system is always stable because we have minus zeta omega n as a real part, and since zeta is positive, omega n is positive, so minus zeta omega n is always negative, and we have always a stable system. And for the third one, it says it's asking for which condition we have overshoot in the response. We have overshoot the response if our system is underdamped or if the damping ratio is less than 1. For the part B of the fourth question, it has been a closed loop unity negative feedback closed loop system is given, and we have a controller proportional from derivative. In the first part of the question is asking to find transfer function h of s based on the response given here in this picture, and it has been said that we have the h of s is the first order system. And for the second part is asking to find the reasonable value of Kc for which the closed loop system will be stable. So let's first solve the first problem. For the first problem, we know that for the first order system, the response is the format of beta e minus alpha t. Here beta and alpha are known, when we need to find the beta and alpha. If you look at the graph, we have at t equal to 0, y0 is 4. So if we substitute a 0 in this relation, we will get y0 equal to beta e power 0 equal to 4. So since e power 0 is 1, we will find beta equal to 4. If we look at another point, for example, t equal to 1, from the graph we know that the y1 is equal to 0.5. And if we substitute t in this relation, we see that y1 is equal to 4 e minus alpha equal to 0.5. In order to find alpha here, we need to take the ln from both sides. So ln of e power minus alpha will be equal to ln of 0.5 over 4. If we solve this one, we find alpha equal to 2.079. So the final format of the response is yt is equal to 4 e minus e power minus 2.079 t. So if yt is in this format and we found the beta and alpha already, assuming this response is given for an impulse function, so the transfer function h of s will be beta over s plus alpha. If you look at the closed loop transfer function and we find the equivalent transfer function of the closed loop system, we have kc plus s multiplied to h of s over 1 plus kc plus s multiplied to h of s. If we substitute the transfer function of h of s in this relation, we will get kc plus s multiplied to beta over s plus alpha over 1 plus kc plus s multiplied to beta over s plus alpha. If we do multiplication and we have this fraction will be equal to kc plus s multiplied to beta over s plus alpha plus kc plus s over beta. If we further simplify the denominator, the transfer function will be in the form of kc plus s multiplied to beta over 1 plus beta s plus alpha plus kc beta. Since the stability of the system is just related to the poles of the denominator, we just look at the denominator part. So the poles of the system is equal to minus alpha plus kc over kc beta over 1 plus beta. In order to have a stable system, these poles should be negative. So we put this one less than 0. In order that this fraction be less than 0, since we have minus here, it means that the alpha plus kc over beta over 1 plus beta should be bigger than 0. From the first part of the equation, we know that beta is 4. It has a positive value, so 1 plus beta is bigger than 0. In order this the total fraction be bigger than 0, alpha plus kc beta should be bigger than 0. If I solve this inequality, I will get kc should be bigger than minus alpha beta. So for the values at which kc is bigger than 0 minus 0.52, the system will be stable. So this is the solutions for the question 4 of sample exam. I hope you find this presentation useful for preparing yourself for the final exam. Have a good day, and I will solve further questions in my next video. Bye for now.